let's go over the domain and range of all of the trig functions. So first, let's once again write out the general definition of trig functions. If you're following along in the playlist, this is not the first time we're doing this, but it's good practice to spell out this definition multiple times. It's good repetition because that's probably the main point of this entire course, that you understand the definition of trig functions. So, okay, the general definition of trig functions. This is the general definition because it applies to any angle from 0 to 360 degrees or beyond 360, or negative angles, any angle from negative infinity to infinity, this definition applies to. As opposed to, you can think about just looking at a right triangle, the acute angles of a right triangle, the classic SOHCAHTOA, sine is opposite over hypotenuse. That's another perspective of looking at the definition of trig functions, but that's a little restricted because you're just considering acute angles. This is the general definition. So you start by drawing an XY Cartesian coordinate system. Then we're going to think about an angle in this coordinate system, any angle that's in standard position. Standard position means the vertex of the angle is at the origin, and the initial side is in the positive x direction, and the terminal side is anywhere in the xy plane, anywhere. And then with the angle between the initial side and the terminal side being positive if it's counterclockwise and negative if it's clockwise. So what we're going to do now is draw a terminal side at just some random position in the 2D plane here. This is completely random, so let's go ahead and do the third quadrant. Why not? It doesn't matter. So what I mean by that is what the rules that we're laying out here apply to any quadrant, any angle, any positive, negative, quadrantal angles. So an angle that's 90 or 180 or 270, etc. So here's this angle, theta. Okay, next what you do is you pick any point along this terminal side, because this terminal side extends off to infinity. Its endpoint is at the origin, and it extends off to infinity. So we're going to pick any point other than the vertex along this line. The point doesn't matter. So we'll pick this point. And then next, we're going to create a right triangle that has hypotenuse being this segment going from the point to the origin. So this would be the hypotenuse, but we're going to call this R. And the right triangle that we're going to create is going to have the perpendicular side attached to the horizontal. Now again, this exact process of picking this point and creating the right triangle, etc., applies to an angle in any position, in any quadrant. Now next, we want to label the side lengths of the triangle based on the coordinates of this point. And we want to specify if a side length is negative or positive. The side lengths of a triangle in general can't be negative, but for this definition setup we have here, we can think about it that way. So this side length is going to be negative y. It's in the negative y direction. This side length is going to be negative x. But if you were in the second quadrant, you'd have a positive y and a negative x. First quadrant, the side lengths would be positive x, positive y, etc. In fact, though, we could just write it. We don't want to put negative x. We'll just put x and y, and we'll let the coordinate system dictate the sign. So, in other words, to get to this point, you have to go in the negative x and the negative y. So just put the x coordinate and the y coordinate, and the negative will automatically be there. There's no need to put to actually include the negative. Okay. Now, r, based on the Pythagorean theorem, the magnitude of r for any angle will always be positive because r is equal to the square root of x squared plus y squared, always a positive quantity. All right, now with this triangle set up, the next step is you come to this acute angle within the right triangle, whose vertex is the origin, and you do SOHCAHTOA to get each of the trig functions. But keep in mind, we are not finding the trig functions of this angle. This is just a technique. We just come to this angle and do SOHCAHTOA, but we're not finding the trig functions of this angle because the side lengths could be negative. The only way we would actually be finding the trig functions of this angle within the right triangle is if we ignored the negative signs on the y and the x. We're finding the trig functions of this angle. So, for example, the sine of this angle would be the opposite over the hypotenuse. That's going to be a negative y over the radius, as opposed to the sine of this actual angle would be the positive. This as a positive over the radius. Okay, and so with that, we can define the trig functions, and this is for any angle, to be sine of theta is equal to y over r. But this is general for any angle because y could be negative. It's just the coordinates of y. It's the coordinates of this point, positive or negative. Cosine of theta is equal to x over r, and tangent theta is equal to y over x. And then the other trig functions we could get using the reciprocal identities. So secant theta, the reciprocal of sine, is r over y. Cosecant theta is r over x. Cotangent theta is x over y. Okay, so there's another really good slow development of the definition of the trig functions. It's good repetition to do that more than once. So now, what are the domains and ranges of each of these? Well, okay, if you think about the general definition, the first thing to note is if we're not at a quadrantal angle, if we're not at 0, 90, 270, or 180 or 270 or 360 or or anything coterminal to those, if we're not at a quadrantal angle, then we're always going to have a right triangle that has side lengths that aren't 0. They might be negative, but that's not a problem if they're negative, right? There's no issue with these ratios with negative numbers. So as long as there's the side lengths are non-zero, all of them, then every one of these trig functions is going to exist. It's going to be a number. And so what that shows you is that if it's not a quadrantal angle, then there are no domain issues for any of the trig functions. Okay, great. So we just need to think about what happens at the different quadrantal angles. So how do we interpret a quadrantal angle in the context of this definition with the right triangle? Well, we still imagine that that we're dealing with a right triangle at the quadrantal angle, but we just kind of think about that triangle has collapsed to like a line. So, okay, let's think about 90, coming into 90. So you've got, so if this is the theta, okay, there's the terminal side, there's theta, okay, so and this is the initial side. And so the same process, we pick any point along this line, and then we create a right triangle that has the perpendicular attached to the horizontal axis, and then you just put the xy coordinates of that point. So for the first quadrant, these are actually going to be positive, right? And then r is always positive. And so what's happening is, once this angle would get to 90 degrees, the x has become 0. The right triangle has collapsed, and the y has become equal to r. That's what happens. And then you might say, okay, is it the exact same thing at 270? It's very similar. The x becomes 0, but the y doesn't become r, it becomes minus r. That's the only difference, because y is in the negative direction. R is always positive for any angle. That's the only difference. Okay, and then it's an exact same idea, just with, like, if you're coming into the horizontal. So there's the terminal side, the angle theta. Pick a point, any point along this line, and then create the right triangle with the horizontal, the perpendicular attached to the horizontal. And you can see that so here's x. In this situation, x is going to be negative. Here's y is positive. But as you get to 180, y is becoming 0, and x is becoming equal to minus r. Okay, so that's how we're thinking about what's happening at the quadrantal angles. And so with either x or y becoming equal to 0 at a quadrantal angle, that's where there's domain issues come into play, because you could potentially be, with some of the trig functions, you're going to be dividing by 0, which you can't do that, right? Now, but the first thing to note is that the r never becomes 0, because even like if y becomes 0, you still have it's r is equal to the square root of x squared, right? So r is never 0. And so what you can notice about that then is, well, look, you have sine theta and cosine theta are divided by r. R is never 0. Okay, so then, well, what about y and x? Well, y and x could be 0, but so what? If r is never 0, then sine theta and cosine theta have no domain restrictions. The domain of sine theta, and cosine theta are just negative infinity to infinity. Okay, now tangent, you're dividing by x, so we just have to look for what quadrantal angles is x 0. That's just any angle along the vertical. So the domain of tangent is that x can't be equal to 90 or 270, and then, but you can, or any angle that's coterminal with 90 or 270, right? So 360 plus 90. But any other angle is fine, because x isn't 0. And if y is 0, that doesn't matter as long as x isn't 0. Now with cotangent, it's just that the y can't be 0, and that happens only at horizontal angles. So x, or that would, okay, this is theta. So theta can't be 0 or 180, or any angle that's coterminal with these angles. Okay, now secant and cosecant, it's the exact same idea as tangent and cotangent. When can you not divide by y? For secant, it's at these angles. Theta can't be 0, 180, or any angle coterminal with those. Cosecant, you can't divide by you can't have x equals 0, so that's here. Again, or any angle coterminal with those. It's really important. I tempted to write it out with the full n definition, like, you know, any n times 90 or however you would write it, but I'm just going to leave it like this. Okay, great. So that's the domains, but what about the ranges? Okay, so let's think about sine. So sine is opposite over hypotenuse. It's always the y over the r, right? It's not like the angle, depending on the quadrant, can be oriented in a certain way to where the opposite is the x value. No, it's always the y over the r. Well, okay, if you think about that then, so the y over the r is always the leg of a right triangle divided by the hypotenuse. Then no matter what, it doesn't matter what r you pick, how large you make the r, y is never going to be greater than r, ever. At most, it will be equal to r. So what that tells us is that when it comes to the range, sine will never be greater than 1. It could be equal to 1. It could be equal to 1 at theta is equal to 90 degrees when y becomes equal to r. When y is equal to r, you have r over r is equal to 1. And then it could be equal to 0 because y could be equal to 0 at the horizontal, right? At the horizontal, y is equal to 0. 0 divided by r. R is never 0. R is always positive, never 0. Because remember, the point that we pick can't be the vertex. So r is never 0 or negative. But y could be 0. So we could get values from 0 to 1. But then we could also, though, have, when we come below the x-axis, we could have negative y values. But even the negative y value is always going to be less than r, or at most equal to r. You'll have negative r, or y is equal to negative r. So what you can see is it's the range is, you're always going to have something between -1 and 1, including -1 and 1. So the range is -infinity to -1, including -1, in union with 1 to infinity. Okay? Now, cosine is going to be the exact same logic. It's going to have the exact same range as sine for the exact same reasons, except you're just talking about the horizontal leg. Like, it's the horizontal leg is never going to be greater than the radius, the hypotenuse. It's the exact same logic that we just talked about for what the range of sine theta is why the range of cosine theta is the exact same range. Okay. What about tangent? All right, well, if we come to the first quadrant, let's think about what's happening in the first quadrant. So when you're at 0, you have x is equal to positive r, x is equal to r, y is equal to 0, so tangent is 0. Okay? Then as you start increasing theta, what's happening from 0? Well, the x is starting to shrink. And as you keep going, x is shrinking and shrinking and shrinking all the way to 0 once you get to 90, right? And what's y doing? Y is increasing towards r. So you're going at theta is equal to 0. You've got it's y is 0 and x is r. And then at theta is equal to 90, you're making a transition to where you're going to this, r over 0. Well, r over 0, that's infinity. So you've gone from 0 to infinity, positive infinity, right? You could get infinitesimally close to theta is equal to 90, and so you could get any number, right? So like the idea is you could, going from 0 to 90, you could get any positive number for tangent, any positive number. Pick any positive number you want, and you could solve for an angle theta for tangent that like to where the tangent of that theta gives you that positive number. Okay, but is that it? So is the range 0 to infinity? Well, no, it actually, we could get any negative number as well. We could get any number from negative infinity to 0 for the exact same idea. You would, so here's infinity, and then y over x would shrink back down to 0. But then going in the other direction, you're going to go from 0 to negative infinity, and then from negative infinity back to 0. Why? Because the y is going to be negative. Here, you would go 0 to infinity, and then you wouldn't go from infinity to 0. Here, you would be y over x. X is negative. You would actually be you would flip to negative infinity. So it would be like a vertical asymptote. So here's 0 to 90, and then you cross the vertical asymptote, and you'd be here. Right when you cross over, the tangent would not exist at theta is equal to 90, and then right when you cross theta is equal to 90, you'd be at negative infinity, because you'd have like a y is equal to something positive close to the radius divided by a tiny negative number, and then that would increase all the way to 0, and then it would continue to increase all the way to positive infinity, because it's negative divided by negative, you see? And then you'd flip here, it would go negative infinity back to 0. So, but what you can see is that the range is all real numbers for tangent. You can get any number. Okay, cotangent is the exact same logic as what we just did for tangent, except it'll just be, now you're thinking about when y becomes 0, like your cotangent is going to 0 at the vertical and infinity's at the horizontal. But it's the exact same logic. Okay, now what about secant and cosecant? Now you kind of think, well, that's going to be the same as like sine and cosine, right? Actually, no. These are going to be like the exact opposite of the range of sine and cosine. So, all right, let's start in the first quadrant and think about. So we're at theta is equal to 0. What's happening there? Well, and we'll think about secant. Well, you've got r divided, well, y is 0, so you're at like infinity. If you just go to like a tiny positive angle, that's positive infinity. So what about at 90? Well, there you've got y is equal to positive r. You have r divided by r, so that's equal to 1. So you go from 90, from theta is equal to 90, you're at secant is equal to 1. And then when you go down to 0, it's positive, and you go to positive infinity. Okay? So what happens when you go past 90? Well, then, okay, r divided by y, so r is like some finite number, but y is shrinking all the way to 0. So you go to positive infinity again. You go positive infinity to 1, and then back to positive infinity. Now, if you have an angle that's a little bit, just slightly bigger than 180, you've got r divided by a tiny negative number that's negative infinity. And then when you get to 270, you've got r is equal to negative y. So secant is negative 1, and then you go to negative, and then as you go to 360, you get to negative infinity. So what you can see there is secant is going to have a range of negative infinity to 1, or to negative 1, including negative 1, in union with 1 to infinity, which is like, it's like the opposite of this, right? Oh, wait, I'm sorry. I don't know what I put here. This should be, this is negative 1 to 1. The range, you could only get a value between, for sine theta and cosine theta, the output can only be negative, something between negative 1 and 1, including the endpoints. And then the output for secant is like the opposite. You can get anything outside of this range, but actually both include 1 and negative 1. Okay? Now, cosecant is going to be the exact same range. And you could do it's for the exact same type of analysis that we just did for secant. And so there you go. That's the domain and range of all of the trigonometric functions.